I think it's more realistic to do it.
Yeah.
But I did it as well.
Yeah. I don't think it makes it.
And also, I love Stefan referring to all of these.
Stefan's going to be like, yeah, that's okay.
Yeah.
Okay, cool, I'll give you 69, you 70, you 71. Everyone's happy now.
Random,
He doesn't
random
get
number
it.
generator.
Just with it like 5%
That's
margin
what
of
Elliot's
70.
banking on anyway.
Except Elliot will be the one to prove that he did mark it harshly. He'll be like 55.
Starting today.
Elliot, how was it last
What
night?
night was it?
Where did you book it?
Is it living room?
No, it's good.
Is it good?
I didn't go.
Oh.
I've been out for 2 weeks.
Oh no.
We enjoyed it.
What are you going to do?
Open up.
When me and Jack left the library, we thought we'd swing by there and say hello to people, and then we just saw Elliot like, bumbling out for a bit.
So, the concept about
Oh, that, yeah, it was this.
I've got exams for 4 weeks.
Yes.
The next Friday I've got another one. The next Saturday I've got another one. And the next Wednesday I've got another one.
so the concept about
Yeah, we've got to revise this.
response spectra is once you know the building period or bridge period, from here, suppose the period of the bridge or building is here, from you can read off and you can get the acceleration of the structure, and if you know the structural mass, modal mass, in what mode, you can then compute the force on the total building, and that force is taken by the foundation, right? So you can get the force on the foundation. Suppose in example you have got, suppose here you get the piled building, and there are say 20 piles. So the building mass is m. So if I have to get a quick number for the force on the pile, what I will do, so I will find out the building period. Say if it is a 1, 2, 3, 4 story building, my thumb rule will say 0.1 times the number of stories, which is roughly 0.4 second. If I know the ground is say type A or B or C, whatever ground it is, I will choose the right spectrum to that ground, say ground type S. I will choose S curve to match the ground. The codes give you the response spectrum for different types of ground. Type A, type B, type C, type D, S1, S2, Eurocode 8, for all codes. For that matter, they give you a type of ground. So you match the ground, take the spectra, you know the time period, so this value goes here, right? This value goes here. Read the acceleration, you know the modal mass. So the total inertial load, let's say F force is equal to mass times acceleration. Normally first mode is very important. First mode. By first mode I mean, if you look into how we analyze this problem, we assume a beam and here is a lump. Each floor will have a lump mass. That's the model we normally use. Yeah? Yeah? So once you get the mass, and if you know the number of piles, so the force on each pile will be given by this force by 20. Yeah? Right? Because we assume that all the piles are rigidly connected to the pile cap. Normally that should be done. In that case, what happens? The force gets evenly distributed, right? And you don't start to initiate, because if you have this, if one pile fails, this other pile will take that share of load, right? This way you can get a force on the pile. So building mass, you know the acceleration you can get from response spectra, that's the total building inertia, and you get the load on the pile. Yeah? So therefore important is to how to calculate the building period or bridge period, then the spectra. So that is concept number 2. Use of response spectra to obtain force on foundations. Yeah? Okay. Third thing is assessment of liquefaction and ground period. So, for for finding out liquefaction, I think you will be doing it in your coursework. This part you have done it to Stefan, isn't it? Yeah? You have done it to Stefan because if you use the mass matrix, K matrix, that gives you the building time period. Right? That is the sort of theoretical way of doing it. And the thumb rule method is 0.1 times m or Ct times height to the power alpha. That's your thumb rule. Okay? And what happens for a realistic building, for a real building, a very complicated building, not very regular. In that case, you will make a model of the whole building in a software, and you find out the eigenvalue, eigenvector. Eigenvalues will give you the building period. First mode, second mode, third mode, fourth mode. The eigenvector will give you the mode shapes. First mode, how the building would sway. Yeah? Okay? So this links how you link the structural part with the geotechnical part of the whole building design. In terms of liquefaction, now, so what we're doing here is, so when we do a building, suppose we are to do a building here, in this site. Say it can be a nuclear power plant or can be any structure. To what depth do we go normally to investigate? Is thumb rule? Normally the founding level plus something. Why? Because say you have a pine, you go up, say 20-meter pine, right? Yeah? And you just missed that there was a very soft layer there. You just missed it because you didn't go that deep, right? The pile plunged and then you have failure, right? So you normally have to go founding depth of the pile plus few diameters, right? So depending on where, right? So that's the depth. So normally if it is 20 meters or 30 meters, okay, so around that level. So you go up to 30 meters, right? So if I want to do a in scale, so if I do 30 meter in scale, say I do it here, 30 meters, right? The earthquake fault ruptures at what depth? If you look at the epicenter, hypocenter, if you read what they say, at what depth? Kilometers, right? Kilometers. So if I do 30, 60, 90, I go on doing that, somewhere even below there, isn't it? So here the fault ruptures, right? Here a big rupture, way big probability to there, right? So this is the whole problem. So you can't model a 10 kilometer down whole ground and do that, right? That's why we have a concept called seismic base layer, seismic bedrock level, all these things. So meaning, where we stop our analysis thing, where we will cut our domain. So where do we stop? This we assume is like a rigid block or something. Yeah? This is known as engineering base layer. Engineering base layer. So if you use the word engineering, everything is acceptable. The engineering, right? Not science. You say that. Not science, engineering. So you just cut down. Science is there, you can't do it. Right? Yeah? You agree? See, 30 meter, 8 kilometer, there the wave, there you have a big rupture, the waves are traveling from there to here. That shakes the whole building. So you really can't do it, you have to find the way. Now, how do you find out that layer? Where to stop? Again, this is unsaid thing in practice, and you don't find anybody will say, this is the tricks of a consultant. How will they charge you money? So, we know the answer. Come, sign the contract, we will give you the answer. So I found out in Japanese code, in Japanese that they've got some ideas, so which I put it in the notes. You see, in Japanese. So typically n value of 50, depending on the type of structure. Nuclear power plant, n value of 50. You say that's the very stiff layer. In highway bridge, a different number. I think I given in the notes. If you see, there's a in unit 6, there is something called correlations. In that correlations unit, there is that number, right? I can tell you exactly where it is. Okay, that's in unit 6. Correlations. Unit 6 correlations. And there I have given a yeah, so 6.4.1 here. 6.4.1 engineering base layer. Okay? If you look into these notes, 6.4.1 we have defined the engineering base layer. Okay? So basically you find out a way. You basically take from there, right? So what do you assume? You assume that we say the waves is traveling like that, right? And the medium is getting, this is stiff, less stiff, less stiff, less stiff. We're getting soft, isn't it? And each time it comes, it basically move towards. So when it comes near our surface, it is purely vertically propagating waves. Actually, waves travel like if you throw a stone in the water, it moves in that particular way. But as the wave travels, it goes to different soil stiffnesses, it starts to deviate, and when we come near the surface of the earth, it is purely moving in the vertical direction. So basically how it moves, the waves are traveling in that direction. This is S waves, shear waves. So that is the wave propagation direction. Goes up there, reflects back, comes back, okay? And then what happens? So if I now simply have the scale a little bit bigger, that wave, and say that is 30 meters. So as the wave travels, if you take a series of, say, soil elements, so as the wave propagates, these soil elements starts to shear. So this shears in that way, this shear may shear in other way. Okay? This is how the soil deforms. Right? So that's how the soil will deform as it moves up. Right? Now, common sense. The more it deforms, more chance of it to liquefy. What's happening? The soil element, we are trying to deform it, right? Not only that direction, but also this direction, yeah? It also does that. Yeah? There are so many soil particles there, isn't it? So soil particles and water. So that particular motion starts to generate core water. So you see there are increasing core water pressure. And that how it liquefies. So what you can see, the important link is more the deformation, more the problem. More deformation means more acceleration, right? So more shear stress. So what we work out this something called cyclic stress ratio, which is tau by sigma b test, right? So we work out the stress ratio, and again this is a function of acceleration of the earthquake, right? So you can see we need a hazard parameter there. So why we need a hazard parameter? We need to know what is the acceleration, right? And then you can work out the CSR, and for that, but then you can use the code of practice. There's a graph there. If you have a ground level, you work out CSR ratio. You know your ground N value. You see where the point lies there and here, and you can use it to work out your depth of interaction. Yeah. So what you do, you split it into every meter, and then you check, and you say, okay, fine. It is like this depth. Yeah. Okay. So you find a site that the ground will liquefy. What are the options? What can you do about the functions? There are different ways. You can say, well, I will try to have the ground improved. I will try to put some, I will try to have the ground improved so that I can have a higher end band. Then I remove the point, right? So again, then you say, what's the cost of that ground improvement? Right? And you can then think of solutions. So you have the problem identified. Once you know the earthquake PGA, then you identify the problem. Is it liquefiable or not? Yeah? If it's liquefiable, what do you do about it? Shall you do you want to excavate the whole ground and take the foundation to deeper depth with piles there, or you can say, well, I want to have it not improved, or I will have a different solution. Yeah? Is there any question? Did it answer your question of this course performance? Oh, did it? Yeah? Okay, now, ground period. Another ground period, yeah? Ground period. So, I think in exam you often ask a question, what's the ground period? Why it's important? So, what happened in Mexico City, I think I will tell the story about that. So Mexico City, so this thing that ground can amplify the motion was identified in the earth of Mexico. So there was a big lake in ancient times, and now the lake was sort of filled over time, and then now the very big township, a very big city. The whole city was earlier than the lake. Now that means this was the lake. It was filled up over thousands of years. So that means this part is a solid ground, right? So you can imagine, say this block, another block like that, and another block like that, and another block. Just think of same different heights. And think of this, and I've got a table and having jellies of different heights. And if I shake them, some will deform more, some will deform less. And that depends on how I shake it. So exactly what happened there, they found out a certain amount of distance, a certain amount of area, whole buildings failed, everything failed. Next was okay. And they figured out actually, in this location, the ground period matched the period of the earthquake. And that gives a lot of application. That's very important to work out what's the ground period. So, this you can obtain by doing a ground response analysis by software cycling 1D, that software which I told you. Cycling 1D in the previous years is a free software available in the internet. You can download. What you do, you give a ground profile, so you tell the ground profile, and you give your earthquake input motion, and you record the motion here, right? If the period is close to earthquake periods, you see a big movement, right? So, in a simplified way, what you can do to work on the period, say H is the ground here, and Vs is the shear wave velocity of this ground. Do you know this term, Vs? Yeah? So, shear modulus G is equal to density times Vs squared. So, if you know the shear modulus of the ground, you know density, you can find out the velocity. So, in practical terms, you can easily compute that. So if you do a geophysical test, so in a site, big ground, you put two geophones, you record the time taken for the wave to travel from there to there, from there you can work it out. It's a very, very common test that can be done. Remember, this unit is typically in megapascal MPa, right? This we normally have it in meter per second, so try to have the units correctly, otherwise you get wrong numbers. Yeah? Shear modulus of soil is in GPa range, is in MPa range. Yeah? Steel, concrete is in GPa range. Steel is 200, steel, concrete they are in GPa range, but soil is MPa range, megapascal, right? And so, once you, that's the thing. Now, how we can work out this one? What happens there is, if you look into wave propagation, from A-level physics, V is equal to frequency times lambda. Lambda is the wavelength. Now a ground cannot deform in this pattern. So this is the ground H. So lambda is 4H. So therefore V is equal to frequency times 4H. Therefore the frequency of the ground is given by V by 4. That's a very simple way you can use to check the ground period, right? Now the frequency, time period would be inverse of that. So ground time period TG, if you see into all codes of practice, they give you a way to work out by saying 4H by Vs. Yeah? That's the ground period. Yeah? And if you have a layered soil, you simply do summation of 4Hi by Vsi. To what depth you go? You go up to engineering base rate. Yeah? You go up to engineering base rate and you do that one.
What is TG?
Ground time period. Time period of ground. Yeah?
I'm just wondering, because geophysics, it technically doesn't get very deep. You have to do the two nodes, you have to be 7 meters away to get any sort of depth.
Yeah. So they're quite hard.
In practice,
Yeah, but so normally they're used for large projects, very big projects, offshore projects, very big, large offshore projects. Large. So they're usually work out the area.
it's not very practical.
On
Urgent cases.
it's something, but normally you so if you look into the example of what n but just to give you your philosophy, but it's not yes. Yeah, but how do you remember? How do you that's to remember. So the different code they give you the formula for in that case. This is how it comes. Yeah, say you have got a layer system. Okay, so how can you apply this formula? Yeah? Say you get a so you get layer 1, layer 2, layer 3 and layer 4, right? Say this one is H1, H2, H3, H4, VS1, VS2, VS3, VS4. For this ground, you can use the formula, that's summation of, so this ground, so basically what we are saying is that this ground would deform and the ground would deform in this particular way and taking a small element there. So suppose this small element, right, would deform in this particular way. This is before earthquake and this ground would deform in that particular way. Yeah? That's the assumption behind this, that the ground would oscillate and that is the deformation, right? So what happens normally after earthquake, you see a shifting. So there is a permanent displacement of the ground. Yeah? So this is the, so we assume that's the engineering base layer. So for different layers, you find out the height and this ground period, Tg, is given by the summation of 4 Ni by Vs. Yeah? Okay? Now if this period, the typical earthquake periods, do you know what's the typical earthquake frequency? 0.5 Hz to 10 Hz. That's the usual range of earthquake frequencies. But some earthquake may have a different, so basically if you now do a Fourier, all these things, you can see the frequencies. But the energy content is at a particular peak. And that we call a predominant period. So earthquake may have a predominant period. There is a main energy is there. So what they mean by that is, if you plot the earthquake energy in a spectrum, you might find that a lot of energy is in this band, and that is the predominant period. Say this period is a 0.8 second. So it means that there is a lot of energy in that range. And if the ground period is, the ground has a similar period, if these two matches, you get a big amplification, a lot of ground movement, a lot of acceleration will be there. So that means the earthquake period, the main earthquake frequency is matching with the ground frequency. Right? That's why you often check these things. Yeah? Okay, so that covers 3 and 4. And final is the pile formation. Now, is there any questions so far of this part? No? Is it easy? Was it enjoyable? Like not too hard. Yeah? As I said, this is subject you cannot learn it in 4 months. Not learn, of course you can learn, but you cannot master it in fact. But what is important to know the important concepts. And then if you start working, have projects work, you will start to build up your, but you have a rough idea about the whole subject. Yeah? Okay. Now in Pile Foundation, yeah? So Pile Foundation, what I would say, I've given there 5 or 6 problems at the end, isn't it? There are 5 at the end. So if you do them, don't look into the answers. The answers are already in the web, but don't look into them. Just do it yourself. Try it. That will reinforce your learning, and then have a look. Okay. Now in Pile Foundation, what you should check for? Okay, and bend and shear. Shear. Okay. First of all, let's do 2 things. First of all is there can be different types of ground. You can have a clay at the top, then you can have sand, sort of loose sand, and you can have dense sand. Yeah? And this can vary. Clay, then you can vary, can vary. You can have fully sandy soil, right? Now the thing is that you have to have a pile design. That means the pile has to carry the load all the time. What you will get the vertical load from the structure. Let's name this P. Okay? Then you will also get the lateral load on the pile. Let's name it H. This will come from where? Response spectrum. Yeah? You get the lateral load on the pile head. Okay? And then I can convert this problem saying, okay, here is the pile, here is the lateral load, here is the vertical load. Right? Suppose there is no liquefaction, there will be pile bending only, pile bending. There will be bending in the pile. Right? Now, this all depends on, the bending of the pile all depends on the top boundary condition. Right? That means if you have a building so the top part of the pile can rotate, can't, because the building is there. There's a tie beam all around. So this building, if I draw the foundation plan, I will see here the pile cap, then another pile cap, then another pile cap, then another pile cap, another pile cap, another pile cap. There are maybe 4 piles. You then have a column here, a column here, a column here. They are joined by tie beams, right? So it can only, on earth, it only translate laterally. It can't rotate because there are all around tied by beams. So the deformation shape will deform in that particular way. note here, it can translate but not rotating, isn't it? It can translate but is not rotating there. Right? On the other hand, say you have got an example where you have a bridge and for some reason they had a linear sort of 4 piles and had a pile cap, and so there's a single row of pile, like the show of bridge example I've shown there. In this case, that is a bridge deck, and you have the bridge deck here and bridge deck there. In this case, the top part can rotate because there is nothing stopping it from rotating. So in that case, this deformation pattern will be like that, and it can deformation pattern can be like that, and again another one like that, right? So look at the boundary conditions. So it all depends on how you at the top be connected. So when we do the design, the thing to find out is the bending moment in the pile. What is the pile bending moment? You know the bending moment in the pile, you can provide the reinforcement or think about the wall thickness. Right? So how do you complete bending moment of piles? So you're taking into account different load scenarios. Suppose there is no liquefaction, small earthquake, only inertial load. Very small earthquake, no liquefaction. Can happen. If the earthquake is less than 5, you normally won't have liquefaction. So as a thumb rule, less than 5, no liquefaction, 5 onwards liquefaction, problem will start. More than 8.5, tsunami, offshore. So you can see the hazard will increase as you go further, Yeah? Because as you go bigger earthquake, means bigger earthquake means that bigger energy released, means bigger displacement, means bigger problems. Now, so the main thing is to find out the bending moment in the pile bending moment. Okay? So, once you work out the inertial load, then the problem becomes this. So one way to work on the bending moment is you do a model in a software where you basically model the pile as a series of springs